Good day everyone, my name is Roland Martinez and this is a video presentation on angular modulation under ECE121, section E01, Principles of Communications. And our instructor is Engineer Marian M. Sierra. This video presentation will be divided into three parts. For the first part will be the comparison of frequency modulation and phase modulation concepts and comparing them to amplitude modulation. Then for the second part, I will show you the FM and PM signal in time domain, frequency domain, and their mathematical equations. And for the last part, I will show you some examples or sample problems and their corresponding solutions. So first, we need to define angular modulation or angle modulation. So what is angle modulation? Angle modulation is a modulation of carrier signal where its frequency and phase signal is varied with respect to modulating signal. So in modulation, we are varying the three properties of the carrier signal. For AM, we vary the amplitude. For FM, we vary the frequency. And for the PM or phase modulation, we vary the phase with respect to the modulating signal. So angular modulation is classified into two parts, which are the frequency modulation or FM and the phase modulation or PM. So as you can see in the figure, angle modulation can be divided into two parts, phase modulation or frequency modulation. These two classification of angular modulation are related to each other. So this table will show you the comparison of FM or PM to AM. So for the first comparison, FM or frequency modulation receivers have better noise immunity, while for the amplitude modulation receivers are very susceptible to noise. The next comparison will be noise immunity can be improved by increasing the frequency deviation, while on AM there is no such option to improve the noise immunity. And the bandwidth requirement is greater and depends upon a modulation index on FM, while on bandwidth is less than FM or PM and doesn't depend upon a modulation index for AM. For FM or PM transmitters and receivers, they are more complex than for AM, while in AM or amplitude modulation, transmitters and receivers are less complex than FM or PM. All transmitted power is useful, so FM is very efficient, while in amplitude modulation, power is wasted in transmitting the carrier and double sidebands in DSB. But this can be addressed using DSB-SC or a double sideband suppressed carrier. So what is a frequency modulation or FM? So FM is the process of varying the frequency of the carrier signal with respect to the modulating signal or the intelligent signal. So as you can see, this is the graph in time domain. So the baseband signal or the intelligent signal is a sinusoidal wave with uniform amplitude and uniform frequency, while in the FM signal or the carrier is varied with respect to the baseband signal or intelligent signal. You can see that the frequency is varied depending on the positive or negative amplitude of the baseband signal. So for the positive, with respect to the baseband signal, the frequency is higher than the negative amplitude of the baseband signal in the FM signal. So for the FM signal in frequency domain, the graph shows that the 1 kHz sinusoidal baseband signal or tone modulation and 10 kHz carrier, you can see that there are many amplitudes going on in the plot. We can see on the left side that the frequency or the bandwidth is the same on the right side, and they are symmetrical to each other. For the FM signal equation or the mathematical equation for a baseband signal or x of t is equal to the amplitude of the carrier times the cosine of the 2 pi omega t plus 2 pi kf multiplied by the integral of negative infinity to time x of t dt, where kf is the frequency deviation constant in Hertz volts, a constant envelope signal with varying frequency and phase. The instantaneous frequency is f of t, which is equal to the frequency of the carrier plus the kf x of t, or the baseband signal. And the maximum frequency deviation is equal to delta f, or equal to kf multiplied with the absolute value of the x of t, or the baseband signal. The deviation and bandwidth in FM. Instantaneous frequency is equal to the frequency of the carrier plus the kf of the baseband signal. And frequency deviation or delta f is equal to the kf multiplied by the baseband signal or x of t. And the maximum frequency deviation or delta f is equal to the kf times the absolute value of the maximum x of t. For tone modulation, delta f is equal to the kf times amplitude of the modulating signal. Deviation ratio will be equal to d, which is equal to delta f over the maximum modulating frequency. For tone modulation, modulation index is b, which is the f over the frequency of the modulating signal. If b is less than 1, the FM is a narrow band or NBFM. When b is greater than 1, the FM is a wideband or WBFM. And to get the bandwidth, BW is equal to 2 times D plus 1 times the maximum modulating frequency. So next is the phase modulation or PM. So PM or phase modulation is the process of varying the phase of carrier signal with respect to the modulating signal. So this is the PM signal in time domain. So as you can see, the baseband signal or the intelligence signal is similar to the intelligence signal you've seen in the FM. The modulating signal has an amplitude of uniform amplitude, and the frequency is uniform. Where in the PM signal, when the carrier is varied, when the phase of the carrier is varied, the modulating or the phase modulation can be moved to the right or to the left. As you can see, it is same with the FM signal, but the phase is shifted to the left or to the right. So for PM signal frequency domain, the same sample as we use in FM for a 1 kHz sinusoidal baseband signal or tone modulation and 10 kHz carrier, FM and PM have the same wider than AM or DSB signal of spacing in 10 kHz. PM signal equation, or the mathematical equation of the PM signal, the baseband is x of t, where where the phase modulation of x of t is equal to the amplitude of the carrier multiplied by the cosine of 2 pi of the angular frequency, or the frequency of the carrier times with respect to time plus the kp multiplied by the baseband signal. Kp is the frequency deviation constant in rad volts, while a constant envelope signal with varying frequency or phase. The instantaneous phase is theta t is equal to 2 pi times the frequency of the carrier signal multiplied by the time plus the kp times the baseband signal, or x of t. So next is the comparison of frequency modulation to phase modulation. So as you can see, in the left side is the frequency modulation, while on the right side is the phase modulation. So the characteristics of frequency modulation is compared to the characteristics of frequency modulation. So for frequency deviation is proportional to modulating signal, or m of t, in the FM, while in PM, phase deviation is proportional to modulating signal, and the noise immunity is superior to PM and of course AM. So noise immunity better than AM but not in FM. So PM is in the middle of AM and FM for noise immunity. So FM is widely used for commercial broadcast radio from 88 megahertz to 108 megahertz, while PM is primarily for some mobile radio services. So for the modulation index is proportional to modulating signal as well as modulating frequency in FM, while in phase modulation, modulation index is proportional to modulating signal. So for the first problem, a sinusoidal modulating waveform of amplitude of 5 volts and frequency of 2 kilohertz is applied to FM generator, which has a frequency sensitivity of 40 hertz volts. Calculate the frequency deviation, modulation index, and bandwidth. The solution is, first we need to get the frequency deviation using the formula delta F is equals to KF AM, where KF is equals to 40 multiplied by the AM time, or of 5. 40 times 5 is equals to 200 hertz. For the modulation index, or beta, is equals to delta F over F of M is equal to 200 over 2 times 1000, which is equal to 0.1. So for the bandwidth, BW is equals to 2FM, that is equal to 2 times the modulating frequency of 2 kilohertz. Next problem will be the given modulating signal produces 50 kilohertz frequency deviation, and the law stated that the maximum frequency deviation allowed is 75 kilohertz. Compute for percent modulation. First, we need to get the given parameters for the actual frequency deviation is equal to 50 kilohertz. For the maximum frequency deviation is equal to 75 kilohertz. So to get the percent modulation is equal to the actual frequency deviation over the maximum frequency deviation, and that is 50 kilohertz over 75 kilohertz multiplied by 100, and the result is 67%. For the third problem, determine the deviation ratio and bandwidth for the worst case modulation index for an FM broadcast band transmitter with a maximum frequency deviation of 75 kilohertz and a maximum modulating signal frequency of 15 kilohertz. So using the given parameters, delta F, or the maximum frequency deviation, is equal to 75 kilohertz, and the maximum modulating frequency of 15 kilohertz, and the deviation ratio is equal to the maximum deviation frequency over the maximum modulating signal, and that is equal to 75 kilohertz over 15 kilohertz, and the ratio is 5. For the last problem, for the practical bandwidth, a 2 kilohertz audio signal modulates a 50 megahertz carrier signal and causes a frequency deviation of 2.5 kilohertz. Calculate the bandwidth of the FM signal. So the given parameters are the modulating signal of 2 kilohertz with a frequency carrier frequency of 50 megahertz and frequency deviation of 2.5 kilohertz. First we need to determine the modulation index to decide if we need to use the Carson's rule using the frequency deviation or the original bandwidth equation. The modulation index of this problem is equal to the frequency deviation over the modulating frequency, and that is 2.5 kilohertz over 2 kilohertz, and the resulting modulation index is 1.25. And according to Carson's rule, if the modulation index is less than pi over 2 or 1.57, then the FM signal will not depend on the frequency deviation. So that in here, the modulation index is less than 1.57. Therefore, we need to use the original bandwidth equation, or the practical bandwidth that is equal to 2 times the modulating frequency, and that is 2 times 2 kilohertz, and the result of, or the bandwidth, is equal to 4 kilohertz.